Can you see the material?
Yes, ma'am.
So today we'll start discussing continuous distributions. The first one is uniform distribution. It's a very simple one. So we should start our discussion with this particular distribution or density function. So the simplest continuous random variable is uniformly distributed. It is used to model experiments in which the outcome is constrained to lie in a known interval, known closed interval, say A to B. So all the outcomes will lie within this particular interval, and the outcomes are equally likely, right? So these two conditions have to be satisfied. Then we say that X is uniformly distributed in the interval AB, and this condition will be satisfied, that is A and B are, rather B is greater than A. We are assuming B to be greater than A, and A or B are greater than minus infinity, or their range is basically from minus infinity to infinity. So with this introduction, let's try to define the density function. So the corresponding density function fx will be given by 1 by b minus a. So this is the density function. Let me show you. This is the density function. So you see that this density function is defined over this interval a to b, right? Now, in this particular region, the density function is 0, as well as in this region, the density function is 0. So that can be expressed with the help of two-step functions. So the density function is actually 1 divided by b minus a. But precisely we can write it as 1 by b minus a ux minus a minus ux minus b. Okay. So to make it simple, obviously we represent the density function to be equal to 1 by b minus a. So this height will be equal to 1 by b minus a, and the region already we have discussed is, that means the value of the random variable x, or any instantaneous value of the random variable x, will lie between this. Within this region. So do you have pen and paper with you? Hello.
Yes, ma'am.
So if this be the density function, then find out the distribution function. So how to find out distribution function? That we'll have to integrate this density function to get the distribution function, or for the time being, just to verify the fact that this is going to be the distribution function for uniformly distributed random variable, that is capital Fx is equal to x minus a by b minus a within this region. So you can take the derivative of this one to verify whether yes, this is the distribution function or not. Please do it.
Yes, ma'am, done.
Okay. So since this is the cumulative distribution function, hence if x is less than equal to b from this part onwards, if is x is equal to b or greater than b, the cumulative distribution function will have a value which is equal to 1, that is the total probability, right? And When x is less than a, the distribution function will assume values which are zeros, right? And from a to b, the distribution function will increase like this. Okay. So from this density function itself or distribution function itself, it's clear that the random variable in this case is a continuous random variable. And from this diagram or from this expression, it's clear that 1 minus fx will be b minus x divided by b minus a. Please check whether this relation is correct or not. And this relationship is valid within this region. Got this expression?
Yes, ma'am.
So 1 minus fx can be drawn very easily, and this is the plot of 1 minus fx. Now, the expectation of this density function fx, ex can be computed as, per definition, that is, expectation of x is equal to integration minus infinity to infinity x fx dx, right? Now fx, we know fx is given by 1 by b minus a. Hence, within this integration part, it will become now the limits of the integration will be a to b, and this one will be, this term will be x by b minus a dx. So if we perform the integration, it's quite straightforward. So we'll find that expectation of x is equal to 1 by b minus a. We can take this out from the out of the integration sign. So this one will be x square by 2, and the limits are a to b. So the result of integration after taking limit will be 1 by b minus a, b square minus a square by 2, and hence the expectation of this distribution will be a plus b divided by 2. Similarly, we can find out the variance. Please go through this. The derivation has been done. So please go through this. The variance, we know that sigma x square is equal to expectation of x square minus expectation of x whole square, right? So this part already, the expected value we have already computed, which is equal to this one, right? Only we'll have to find out this part, that is expectation of x square, which is nothing but 1 by b minus a integration a to b x square dx. Please go through this and please check whether the end result is correct or not. Complete? Should I continue?
Yes, ma'am.
Okay. So the moment generating function will be given by expected value of e to the power sx, right? That means if you want to find out the expected value of this function of the random variable, so it will be integration e to the power s x fx dx, right? So fx, we know that it is equal to 1 by b minus a. So the expected value of this function will be integration over this interval a to b, and it will be e to the power sx by b minus a into dx. So again we can take this out. So it will be e to the power sx by s, and the limits are a to b. So the moment generating function will have an expression which is given by this equation u 1.8. U stands for uniform distribution. So it's e to the power sb minus e to the power sa divided by s into whole b minus a. So similarly, from this moment generating function, we can also write down the characteristic function. So your assignment is to find out the expected value of this distribution as well as the variance from this moment generating function, either from this moment generating function or from this characteristic function, right? And try to corroborate those two values with the values that you have obtained while you have computed the expectation and the standard deviation using the basic definition. Is it clear?
Yes, ma'am.
So it's written over here. Now, one of the important applications of the uniform distribution is in describing the errors associated with A to D conversion. Have you studied A to D conversion, analog to digital converter? Hello, have you studied analog to digital converter?
Yes, ma'am.
So you must be knowing that what is meant by quantization noise or quantization error. Okay. So in A to D converter, what is done? We take a continuous signal that can have any value at a given time instant and convert it into a binary number having a fixed number of binary digits. Okay. So let me show you. So here we are discussing analog to digital converters and uniform quantizers rather. And in quantizer or analog to digital converter, quantization noise or quantization, actually the quantization error generates the quantization noise. So that is the problem, and this quantization noise or quantization error creeps in because of sampling and quantization effect. First, let me show you the. So this is an analog signal. As you can see, this is an analog signal. Here we have used several levels, and the voltage value of these levels is specified over here. That is, the peak to peak voltage value is 4 minus 4 volts. That means 8 volts. So maximum positive value is 4 volt, and the sorry, minimum value is minor 4 volts, and these are the levels that we are using, and the associated voltage values are like this: minus 3.5 volt, minus 2.5 volt, minus 1.5 volt. so and so forth, right? Now you see, if we take a sample of this analog signal at this very instant, then we see that the natural sample value is 1.3. And since you have studied analog to digital converter, already you have studied analog to digital converter, we know that this natural sample value should should be either truncated or rounded off, with respect to this level or this level, right? Now, since the value is 1.3, so this natural sample value is close to this particular level, which is the voltage value of which is 1.5 volt, and the quantized sample value is considered to be 1.5 volt, right? So you see there is a difference between this natural sample value and the quantized sample value, and this actually results in the quantization error. In the second case also, you can see that the actual natural sample value is 3.6 volt. We'll have to truncate that, and the truncated value or the quantized sample value will be equal to 3.5 volt. And since here we have used 8 levels, 2 to the power 3 is equal to 8, 8 levels we have used. Hence, finally, this quantized sample values could be coded or could be written with the help of sequence of zeros and ones. The first one will be 1.5. 1.5 corresponds to this particular level, level 5. So its sequence will be 101, and we have used 3 bits for representing this quantized sample value. Okay, so signal to noise ratio actually here will not be calculating the signal value, will be calculating only the quantization noise value, and the quantization noise or quantization error can be computed by finding the variance variance of the distribution, right? So here you see the quantile intervals are equal to q volts. The levels are q divided by 2, minus q divided by 2, 3q divided by 2, 5q by 2, so on and so forth. These are the levels, and here we are using L number of levels. L number of levels, right? And for uniform quantizer, this difference is known as quantile interval, and for uniform quantizer, this quantile interval should remain constant. As you can see here, the quantile interval is equal to q volt, here the quantile interval is equal to q volt, so and so forth. So now we can find out the error, considering we are assuming that the actual analog signal can assume any value within this quantile interval, or within this quantile interval, or within this quantile interval. Okay, so that's why we are assuming that this random phenomenon actually is following uniform distribution. Okay, so let us assume that the quantization error E is uniformly distributed over a single quantile interval, which is q wide. That is, the analog input takes on all values with equal probability within this quantile interval. So then the quantization error variance, which will actually give us the quantization noise or quantization error in general. So the variance sigma square will be equal to integration over this interval minus q by 2 to plus q by 2. So here minus q by 2 is equal to the value a, and plus q by 2 is equal to the value which is b, right? So we are trying to estimate the error within this two ranges, within this range rather. So, and let's assume that the error is e, that means 1.5 minus 1.3 volt, so on and so forth. So e square, since we are trying to calculate the variance, hence it will be E square into probability of error. Probability of error, and here we are assuming that probability that the random variable x will have a value E, and remember that here the random variable x is continuous. It can assume any value within that particular interval, and that will be equal given by 1 by q. Remember, fx was equal to 1 by b minus a. So the probability of error e will be equal to 1 by q, and it's uniformly distributed, right? So here we'll get integration. If you want to find out this variance, so that will be integration minus q by 2 to plus q by 2 is square 1 by q, as this one is equal to 1 by q d. And if we perform this integration and if we put the limits, then the quantization will come out to be equal to q square by 12. Please check. Got the result? Have you got the result?
Yes, ma'am.
So here we have just calculated that quantization error, and the error variance will be equal to q square by 2, where q is the quantile interval in volt, and this is the standard deviation. Have you understood this? Have you understood this?
Yes, ma'am.
Next one is exponential distribution. Right? So for exponentially distributed random variable x, the probability density function and the cumulative distribution functions are given as, first the density function fx, that is equal to 1 by b e to the power minus, this is minus x minus a by b for x greater than equal to a and 0 otherwise. Okay. So if this be the density function, then by performing integration, we can find out the distribution function fx, and that will be equal to 1 minus e to the power minus x by a divided by whole divided by b for x greater than equal to a, and will be 0 otherwise. So please check this result. Not now. Now, a very common form, very popular form of exponential distribution is this one. Fx is equal to lambda e to the power minus lambda x, as x is greater than equal to 0. So that means 1 by b, if I compare these two expressions, these two equations, then it comes out to be equal to that lambda will is equal to 1 by b, and the value of a is equal to 0. Value of a is equal to 0. So here we'll get an exponentially decaying function which will start from x equal to a. Here, since a is equal to 0, hence we'll get an exponentially decaying function from x equal to 0. So this is the density function, and if this is the density function, then the distribution function can be obtained by taking integration. So integration minus infinity to x f v dv. So that is equal to minus infinity to x integration lambda e to the power lambda v dv, and that will be equal to 1 minus e to the power lambda x. You can forget about this ux. Okay, ux is only for implying or emphasizing the fact that the density and distribution function exist only for x greater than equal to 0. So actually after this particular step, we should work out this particular step and we'll get the final result, which is equal to 1 minus e to the power minus lambda x. So this is a typical exponentially distributed density function, right? And this value at this point x is equal to 0. And the distribution function will be like this, right? Again, 1 minus fx will be like this. Is it clear? Is it clear?
Yes, sir.
Okay, so what is our density function? Our density function is given by lambda e to the power minus lambda x. So from this definition of the density function, we can find out the expected value of the distribution or the random variable. That means expected value of x. Similarly, from this definition itself, we can find out the variance of this distribution, right? So your assignment is to find out the mean and the variance of the density function from the definition of the density function itself. Now next, what we'll do, we'll try to find out, okay, just find out the mean value of this density function, or from the expected value of the random variable from this given density function. Do it. Just find out the mean value. What is the mean value? Hello? What is the expected value? Hello, are you there? Hello?
Ma'am, is it zero?
Mean value, the expected value. This is fx. Do you think that x into fx, and if you integrate that, okay, so will the value will be 0? Is it possible?
No, ma'am.
So in this case, x is valid from 0 only. So the limit of integration will be 0 to infinity x fx dx, right? And fx is given by lambda e to the power minus lambda x. So within the integration, we'll get the term which is equal to x or lambda x e to the power minus lambda x dx.
Is it 1 by lambda?
Yes, that is 1 by lambda. So why do you take so much of time? How did you obtain the value?
Now I integrated the x lambda e to the power minus lambda x and then put the limit.
Was the integration a very complicated one? Yes or no?
No, ma'am.
Okay. Now next, let's discuss the moment generating function for this exponentially distributed random variable. So from the definition, we know that the moment generating function mxs will be equal to the expected value of this function of the random variable, which is e to the power sx, and hence it will be given by integration minus infinity to infinity. Actually, it will be 0. The lower limit will come out to be 0. Uh, is equal to e to the power sx fx dx. That means lambda integration 0 to infinity e to the power s minus lambda x dx, or this will be the result of the integration. And if we put the limits 0 and infinity, then the moment generating function will be equal to lambda by lambda minus s. Please check this one.
Yes, ma'am, it's coming.
So this is the value. Now take the first derivative of this one. From this moment generating function, now we'll try to find out the expected value. So for that, you'll have to take the first derivative of the moment generating function with respect to s, and you'll have to evaluate the first derivative when s equal to 0. Have you evaluated the first derivative at s equal to 0?
Ma'am, 1 by lambda.
1 by lambda. So which method is a simpler one? This one. For finding out expectation, which method is a simpler one? This one or the
Ma'am,
previous
this
one?
one.
This
This
one.
one.
So that is the appeal of the moment generating function or characteristic function, right? So your assignment is to find the mean and the variance and corroborate your results with the previously obtained results. So from this also we can write down that just replacing this s by j omega, we can um, find out the characteristic function, and with the help of this characteristic function as well, we can find out the mean and the variance of this exponentially distributed random variable. Now exponential distribution has got a memoryless property. So what is actually this memoryless property? Let's see. Now, application. First let us discuss the application. If occurrence of events over non-overlapping intervals. So these are some non-overlapping intervals, and these arrows actually represent that some events are occurring in this particular interval, some events are occurring in this particular interval, so on and so forth, right? Like in 1 hour, some calls are arriving at your mobile, some calls are arriving at your mobile in the next 1 hour, so on and so forth. And this zones, this could be time zones or space zones. Anyway, let's consider for the time being that these are time zones. These time zones are non-overlapping in nature. So let's get back to this. If occurrence of events over non-overlapping intervals are independent, such as arrival times of telephone calls or arrival times of bus at bus stops. So in the first 1 hour, it might so happen that two buses have arrived at a particular bus stop. In the next 1 hour, it might so happen that three buses have arrived at a particular bus stop. Now, intuitively, we can appreciate the fact that arrival of these three buses in this time duration, in this time period, is completely independent of the fact of arrival of a few buses in this particular interval, in the previous 1 hour, isn't it? So this arrival of events are independent in nature. So again, let's go through it. If occurrences of events over non-overlapping intervals are independent, such as arrival times of telephone calls or arrival times of bus at bus stops, then waiting time distribution, how long I'll have to wait for a bus to get, in this particular interval, right? So the waiting time distribution of these events are exponential. Already we have seen that. You see, in this case, the arrival of an event that can be modeled with the help of Poisson distribution. Already we have started Poisson distributions. We know Poisson distribution is a discrete distribution, and that can be verified from this fact as well, because we know that either one bus can arrive, or two buses can arrive, or three buses can arrive. So the random associated random variable x can assume 0, 1, 2, 3. So discrete values only, but waiting time is distributed over this interval, complete interval. The waiting time could be 1.5 hour, 1.5 1 hour, like this, right? So this waiting time distribution, the random variable which represents this waiting time distribution is a should be a continuous one, and this waiting time distribution will follow exponential distribution. Is it clear?
Yes, ma'am.
Now, before discussing memoryless property, let's try to find out that why this waiting time distribution is being modeled with the help of exponential distribution. So let's assume that qt represents the probability that in a time interval t in a time interval t, no event has occurred, right? So let's consider this time interval, and qt is representing the fact that in this time interval, no event has occurred. Under such situation, if x be a random variable which represents the waiting time for the arrival of the first event, waiting time for the arrival of the first event, then by definition, probability that the random variable x will be greater than t is equal to qt. Have you understood this?
Yes, ma'am.
So for this time interval t, actually we are waiting for an event to occur, whereas qt represents the probability that in this particular time interval no event has occurred. So when the first event will occur, certainly the random variable x will be greater than t. So probability that x is greater than t, because we are waiting for the first event to occur, will certainly be equal to qt, right? Now let's assume two consecutive time intervals, okay? And let's denote those two by t1 and t2. So if t1 and t2 represent two consecutive non-overlapping intervals, then by the independent assumption, already we have assumed that the arrivals are independent, okay? So by independent assumption, we can write that qt1, that in the first interval t1 no event has occurred, and in the second interval t2 no event has occurred. These two are independent, hence we can write this as qt1 into qt2 will be equal to qt1 plus t2. That means in this interval t1 plus t2 no event has occurred. That is the probability that q is representing over here, q t1 plus t2. So q t1 plus t2 will simply be equal to q t1 into q t2. Do you get my point?
Yes, ma'am.
So this particular equation 1.8, has only non-trivial bounded solution. So equation will be satisfied for t1 equal to 0, t2 equal to 0. So that is going to be a trivial solution. We are not interested about the trivial solution. We are interested only about the non-trivial solution. So for this particular equation, we do have only one non-trivial solution, which is given by qt is equal to e to the power minus lambda t. Do you agree? The right hand side will be e to the power minus lambda t1 plus t2, right? And that is equal to e to the power minus lambda t1 into e to the power minus lambda t2. Hence, from this we can write that, we can verify that yes, this equation is valid. That is qt1 plus t2 is equal to qt1 into qt2. So far, is this clear?
Yes.
So from this we can write that fxt, from the definition of the distribution function, we know that fxt is equal to probability that x is less than equal to t, right? That is the definition of the distribution function. So fxt is equal to probability x less than equal to t will be equal to 1 minus qt, because qt was the probability x greater than t. So this probability or the distribution function, that is x less than equal to t, will be equal to 1 minus this qt, or 1 minus e to the power minus lambda t. Do you agree?
Yes, sir.
So that is the distribution function for exponentially distributed random variable. Already we have seen that, right? And from this distribution function, again, if we take the first derivative, we'll get a function which is equal to lambda e to the power minus lambda t. And yes, by definition, this is the density function for a random variable x, continuous random variable x, which is exponentially distributed. Now, for demonstrating the memoryless property of the exponential distribution, let us assume two time intervals, consecutive time intervals, s and t, and both are greater than equal to 0. So we are interested about the fact that s and t are greater than 0. So let us consider two events, that is x greater than t plus x. That means we are waiting for the first event to occur after t plus s unit of time. And the second event is x greater than s. That means we are waiting for the first event to occur after time t, which is equal to s. I should not use the term time t, because here I have used t. So after this interval, is it clear? So now we are trying to find out this probability, that is probability uh, x greater than t plus s, given that probability greater than s. So what is the meaning of this? Suppose the value of s is 1 hour and the value of t is, say, 3 hours, right? So the first event, this the first term implies that the first event will occur after 3 plus 1, 4 hours, given that the first event has occurred after 1 hour. Is it clear? So this is a conditional probability. So this is a conditional probability, and from the definition of these two events, again I'm repeating, even that the first, or rather the first event will occur. First event will occur after 4 hours, and this one is first event will occur after 1 hour. So from this, it's clear that this event x greater than t plus s is subset of this event x greater than s. So this is the condition. So this event x greater than t plus s is subset of x greater than s. Have you understood this?
Yes, ma'am.
So this conditional probability will be equal to probability x greater than t plus s divided by probability x greater than s, right? So this one, as per definition, already we have computed. We are waiting for the first event. So this one, qt, we have evaluated. So this one will be qt plus s, and this one will be equal to q s. So this is equal to, the numerator will be e to the power minus t plus s, and in the denominator we'll have e to the power minus s. So the result is, that means probability that this particular event will occur, given that this particular event has occurred, is equal to e to the power minus t. Here we have assumed that the value of lambda is 1. Otherwise, it would have been e to the power minus lambda t. Have you understood this? Have you understood why this one is going to be a subset of this set?
Yes, ma'am.
Fine. So these are the two intervals. So probability x greater than t plus s within this time period t plus s, no event has occurred. Probability x greater than s within this time period s, no event has occurred. Hence, this event implies that we are waiting for the first event to occur after this interval only, after this time duration only, and here we are waiting for the first event to occur after this. So this implies that the probability of waiting time is greater than t plus s, given that the waiting time greater than s does not, this actually, this note is basically the explanation of this result, e to the power minus t, or e to the power minus lambda t. So you see, this probability, this conditional probability actually depends upon this time interval and doesn't depend upon this time. So please note that this implies that the probability of waiting time, that should be greater than t plus s, given that the waiting time is greater than s, does not depend on s. It is only dependent on t. So further explanation, how to explain this particular result. Let's assume that x represents the lifetime of an equipment. Then the above equation states that if the equipment has been working for time s, then the probability that it will survive an additional time t depends only on t and not on s. Though the equipment was working for a time s, and we are trying to find out that yes, the equipment was working for this time s, or time period s, what is going to be the probability that the equipment will work, will survive an additional time t. But we find that the probability doesn't depend on this particular time is, how long it was working. So the final probability doesn't depend upon that, and is identical to the probability of survival for time t of a new equipment. That means we can consider that we are trying to find out the probability that a new equipment will survive for this time period T only. Right? Should I repeat? Should I repeat? The memoryless property means the equipment has completely forgotten that it has already worked for this particular time duration, which is S. Okay, so that means as if we are trying to find out the survivability of a new equipment for this time period T. So, in that sense, the equipment does not remember that it has been in use for time S. So, this is basically the memoryless property of the exponential distribution, right? So, even if we try to find out the survival rate of an old equipment, right? So, actually, will uh, face a problem where we are finding out the survival rate of a new equipment, as if we are trying to find out the survival rate of a new equipment or new component. Have you understood this?
Yes.
So we can say that that particular result e to the power minus t, from this result we can infer that probability of failure is independent of aging. So it follows that for a continuous non-negative random variable x, if this particular conditional probability is equal to probability x greater than equal to t. Or in other words, if this equation holds, then we can say that x is following an exponential distribution. So if this equation is satisfied, um, if this condition is held, then we can say that x is following an exponential distribution. So this is the unique feature of exponential distribution. This memoryless property is a unique feature of the exponential distribution only. This derivation is same as the derivation that we have discussed in this particular section. So I'm not going through the derivation. Just let's see. Exponential distribution is very often used in reliability studies as model for the time until failure of an electronic device. So if we go through this derivation, which already we have seen, so we find that the failure probability or rate of failure is independent of aging. Already we have discussed this. So this is a classic example to demonstrate the lack of memory property of this particular distribution. This memoryless property simplifies many calculations, and hence this exponential model is so widely applicable. So under this model, an item that has not failed so far is as good as new. Also, from this conditional probability, we can derive or we can write down this expression. So other distributions, that is, other than exponential distribution, uh, it should not be equation B. The equation number, I'll put the equation number. So the conditional probability will depend on S. It will not be independent on S. That is, the distribution is not memoryless. Do you have any question regarding exponential distribution? Do you have any question? Do you have any doubt regarding exponential distribution? Or should I start discussing gamma distribution? Hello?
Yes, we can start discussing gamma distribution.
So gamma distribution, I guess you know gamma function. We have already studied, probably in maths, we have studied gamma function. So x gamma distribution is also a continuous distribution. Let us assume that x is a random variable which is following gamma distribution. Then the density function for gamma distribution, the density function is given by x to the power alpha minus 1 tau alpha. This is the gamma function. Tau is the gamma function. Tau alpha beta to the power alpha e to the power minus x by beta for x greater than equal to 0 and 0 otherwise. So this is the density function. So from the density function, it's clear that this gamma distribution has two parameters or two arguments. One is alpha and the second one is beta, right? And we'll see that one parameter actually influences the shape of the density function, and the second one actually influences the scale or peak value of the distribution. Here, alpha and beta are greater than 0, certainly alpha greater than 0 and beta greater than 0. And these are the two parameters of the density functions. And tau alpha is known as the gamma function. And we know that the gamma function is given by tau alpha, that is equal to integration 0 to infinity x to the power alpha minus 1 e to the power minus x dx, where alpha is an integer. You have studied gamma function, right?
Yes, ma'am.
So as we have seen, there are two parameters. One is alpha and the second one is beta. This beta is called the scale parameter, and this alpha is called the shape parameter. So for different values of alpha and beta, we'll see the how the density functions look like. Now, let's first find out what is going to be the value of tau 1. And also we know that the gamma function or this integral converges when alpha is positive and defines a function of alpha for positive values of alpha. So let's first define gamma 1. So gamma 1 will be from this expression 0 to infinity x to the power alpha minus 0. So here alpha is equal to 1. So 1 minus 1, that is x to the power 0, e to the power minus x dx, that is, this one will be 1. So what will be the value of this integration? What will be the value of this integration? Will it be equal to
Tell
1?
me, ma'am.
Gamma 1, will it be equal to 1?
Yes, ma'am. Yes, ma'am.
Okay. So next we examine the reduction formula for tau alpha. Now, tau alpha plus 1 will be equal to, from this expression, alpha plus 1. So it will be x to the power alpha into e to the power minus x dx. So if alpha is an integer, then
Alpha tau alpha is coming, ma'am.
yes, pardon?
Alpha into tau alpha, ma'am. Alpha gamma of alpha plus 1 is alpha into gamma of alpha.
You're talking about this expression?
Yes, ma'am.
Yes. So if we consider this expression or this expression, then further we can write this expression, that is gamma of alpha is equal to alpha minus 1 into gamma alpha minus 1, and finally since gamma 1 is equal to, or tau 1 is equal to 1, so the gamma function of alpha will be equal to or factorial alpha minus 1. I guess you know this. This one is factorial. Factorial alpha minus 1. So I guess this expression is correct. Yes or no?
Yes, ma'am.
So properties of gamma function. Very simple. Please check. Gamma. Sorry. Excuse me. Sorry. So tau alpha is equal to, given by 0 to infinity, x to the power alpha minus 1 e to the power minus x dx. And this is the density function. Already we have seen the density function for gamma distributed random variable is given by x to the power alpha minus 1 by gamma alpha beta to the power alpha e to the power minus x to the power beta. So we can, from this we can note the first property, that if alpha less than 1, fxx is strictly decreasing. And also, please check this property. Fx, this density function, will tend towards infinity as x tends to 0. Please check this property. Is it true? And if it's true, then why it's true? That is, the density function fx will tend towards infinity as x tend towards 0. Could you follow me? Please explain why fx will tend towards infinity as x tends to 0. Anyone can answer this question.
It will be of the form of a constant into e to the power x by beta divided by x. It will be of that form. So it will be tending to infinity in that case, as it tends to 0. Because the denominator part, these are all constants.
The denominator part is constant.
So
Why the denominator part will be constant? Beta to the power alpha, I'm not considering this one. But gamma function of
okay, ma'am, I
alpha,
understand.
in gamma function of alpha, there is a term which is x.
Okay,
This
okay.
tau alpha contains x. So how tau alpha will be constant? That is not clear to me.
Ma'am,
You
the
get
exponential function increases much more rapidly than the linear x function. So that is the reason why it will the denominator part increases. So as the denominator part will increase, so that is the
direct
reason.
mathematically, uh, will you not be able to prove this property? What will happen to tau alpha as x tends to 0? Please check the expression and tell me as x tends to 0, what will be the value of tau alpha? What is the value of e to the power minus x?
Infinity. 1.
What is the value of e to the power minus x as x tends to 0?
1.
So what will be the value of tau alpha as x tends to 0?
0.
Are you sure? Are you absolutely sure?
Ma'am, because when x is 0, integration 0 to infinity will be 0 only, no, ma'am.
Right. So as x tends to 0, this tau alpha will tend towards infinity, isn't it? Sorry, this tau alpha will tend towards
0.
0. And that's why fx will become or tend towards infinity. Is it now clear?
Yes, ma'am.
Again, I'm repeating, as x
Shubham
tends
is trying
to,
to say something, but his mic is not working.
yes, pardon?
Shubham is trying to say something, but his mic is not working, I guess.
Your voice is not clear.
Ma'am, the numerator has x to the power alpha minus 1. So
Your
where x
voice
is
is breaking. What
When
you
x
can do, you can derive this, and you can post it in the group because your voice is breaking. Okay, you get my point? Can you hear me clearly?
Yes, ma'am, we can hear you clearly, ma'am.
Now your voice is clear.
ma'am,
Anyway, please check whether this condition, this particular condition will hold or not. Please check.
Yes, ma'am, it will hold.
So if this condition is satisfied, then the denominator of this expression will tend towards 0, and hence this fx will tend towards infinity.
Yes, ma'am.
ma'am, the numerator also contains x to the power alpha minus 1. So if
Hmm.
x tends to 0, then it will be like 0 by infinity. Hey, sorry, 0. 0 by 0. Like, because if it extends to 0, the numerator is also becoming tending to 0, and the denominator is also tending to 0.
So in that case, we'll have to find out a way to either to prove this property, either to find out whether this property is correct or not, or you'll have to put enough justification to prove that this property is not uh, a valid one, a correct one. Do it on your own, and please post. You can discuss amongst yourself using phone
ma'am,
only.
ma'am, here in the expression of gamma function of gamma of alpha, ma'am, here we are while determining the value of gamma of alpha, we are actually integrating from 0 to infinity. So we are actually varying x from 0 to infinity. So, ma'am, and then at the same time, we are also considering that x tends to 0, ma'am. So I couldn't understand that.
I think the variables are, I mean, the x in the distribution function is different. I think in gamma we are using x to calculate the gamma,
Okay,
and
okay.
We are first getting the gamma alpha function after integration, and then we are putting the value of x.
But after integration, it will generate a constant value, no? It will not depend on x. It will only
Okay,
What
depend on
we are trying to
alpha or
get the
something.
I
okay.
think
constant.
that is
Let me interfere. Okay, so do it on your own individually, and you better post it in the group. Okay, and you provide all of you provide your own justification, and from that we'll try to find out what is going to be the correct justifications to prove or reasons to prove this property. Am I clear?
Yes, sir.
Or you can continue your deliberation after this class using phone only, and then come up with a conclusive comment and post it in the group. And also please check this property. As x tends to infinity, whether fx will tend towards 0 or not. I guess this is to some extent a little bit straightforward. This is the second property. As x tends to infinity, fx tends to 0. Now, this is a typical density function where the random variable x is following gamma distribution. Here, the values of the parameters alpha is equal to 0.5 and beta is equal to 1. Beta is equal to 1. So from this density function, it's clear that if x tends towards 0, then fx actually tends towards infinite, isn't it? Whereas if x tends to infinity, then x tends to infinity, then fx is tending towards 0, right? So the plot of the density function is also is also corroborating these two properties. Now we'll have to prove that yes, these two properties are really valid or not, or really valid. You get my point?
Yes, ma'am.
So this is one assignment for you. And now let's see different density functions for gamma distributed random variable. So here alpha is equal to 2. We have taken this alpha. The shape parameter alpha is kept fixed at this value 2, and the beta values, the scale parameters are like 0.5, 1, 2. So you see for beta is equal to 0.2 and alpha is equal to beta is equal to 0.5 and alpha is equal to 2. This is the density function. This is the nature of the density function, right? We are getting a sharp peak over here, a unique peak over here. Now for beta is equal to 1, keeping this alpha parameters or the shape parameter fixed, you see the shape of the distribution function is completely changed. So here there is no peak which is really very pronounced like this one. So this is the density function or look of the density function for beta value is equal to 1, whereas for beta value is equal to 2, you see the density function, the look of the density function is completely different from this density function, or we can say the shape of the density function is completely different from this density function. So the shape of the density function will certainly depend on the on this parameter beta. Check one thing. So sorry, I'm explaining this uh, afresh actually. Here alpha is equal to 2 and beta values are 0.5, 1 and 2. Here you see there is a little bit similarities between the look of the density functions, this one and this one, right? There is a little bit similarities amongst these density functions. Only you see for beta is equal to 0.5, this is the peak value, whereas for beta value is equal to 1, actually we are not getting a very sharp peak like this, a pronounced peak like this. Okay, so we can say that this is to some extent a scale down. Just forget about the previous explanation, I'm extremely sorry. So we can say that this is a little bit scaled down version of this one, etc. As again I'm showing you the beta value is the scale parameter and the alpha value is the shape parameter, right? And in the first figure, the alpha value is constant, which is equal to 2, which is equal to 2. That is the the shape parameter is kept constant. And in this density function, you see the alpha value is 0.5. And the shape of this here, alpha value is 0.5, which is different from 2. And you see the shape of the density function is completely different from the density functions that we have seen in this particular figure. Now is it clear?
Yes, sir.
Now the next, so the next in the next plot again we can see various gamma density functions. The first one is for alpha is equal to 4 and beta is equal to 2. Alpha is equal to 4 and beta is equal to 2, somewhat like this one, not exactly. Now the next one is for alpha is equal to 4 and beta value is equal to 4. So again we have changed the beta value here. Alpha is remaining constant at a value which is equal to 4, and the look of the density function is like this. Now we have changed the alpha value. So this alpha value has been changed to a value which is equal to 10, and the beta value is equal to 2. So now we can compare these two density functions for which the beta value is same, which is equal to 2, and the alpha value is completely different. And you see the shape of these two curves, these two plots are completely different, right? So what is going to be the nature of the density function? That will certainly depend upon alpha value and beta value. Now the next assignment is for gamma distribution function. Purposely, I have not discussed the characteristic function or the moment generating function, or I have not discussed how to find out the expectation and this variance of this gamma distributed random variable x, right? So that is given as your assignment. Prove that the correct characteristic function is given by phi x j omega, which is equal to 1 minus j omega beta whole to the power minus alpha. So we'll have to prove that. Okay. And hence find out the mean, and the values are given over here. Find out that the mean value will be equal to alpha into beta, and the standard deviation or the variance will be equal to alpha into beta square. So that is your assignment. For this distribution function, purposely I have not discussed how to calculate or what is going to be the or I have not provided the derivations for expectation and standard deviation. Now, some spatial cases of gamma density functions are widely used and have spatial names. So, if alpha is equal to 1, have you noted down the density function? The density function for a
Yes,
gamma
ma'am.
distribution. So please to check if alpha value is equal to 1, whether the density function will be this one or not.
Yes, ma'am. It will be this one.
So are you familiar with this expression? 1 by beta e to the power minus x by beta. If we consider 1 by beta to be equal to lambda, then this density function will be equal to lambda e to the power minus x, lambda x. Yes or no?
Yes, ma'am.
So just now we have learned exponential density function and distribution function. So if alpha is equal to 1, then the gamma distribution will reduce to an exponential distribution. Clear?
Yes, ma'am.
Now, in the next one, this chi-square distribution is also a very important distribution, because in the other part we'll study chi-square test, t-test, etc. So if alpha is equal to n by 2, then it will be x to the power n by 2 minus 1, and beta is constant, that is 2. Then what we get is a chi-square density function. Then we say that the random variable x is following a chi-square distribution or chi-square density function. And the density function will be given as fx, which is equal to x to the power n by 2 minus 1 whole divided by 2 to the power n by 2 beta to the power 2 to the power n by 2 into tau n by 2, as alpha is equal to n by 2 e to the power minus x by beta, that is x by 2, for all values of x greater than equal to 0, and the density function will be 0 otherwise, right? So if alpha is substituted by n by 2, we can have different values of n. And if we keep beta value to be constant, and if the beta value is equal to 2, the distribution function that we get, or the density function that we get, is known as chi-square density function. And the chi-square density function, in this particular case, if alpha is substituted by n by 2, then we said that this chi-square density function is of degree n, or the random variable x is said to be chi-square distributed with n degrees of freedom. So these are some of the chi-square distribution functions for different values of n. As you can see, n is equal to 2, 5, 8, 10, so on and so forth. Now, another very important distribution function commonly used in wireless communication, particularly in wireless communication, there are other applications. So the random variable x is said to be Rayleigh distributed with parameter sigma square if the density function is x by sigma square e to the power minus x square by twice sigma square, x greater than equal to 0, and 0 otherwise. Okay, so this is the density function for Rayleigh distribution, or random variable x, which is following Rayleigh distribution function. The density function is defined to be x by sigma square e to the power minus x square by twice sigma square. In communication systems, the signal amplitudes values of a randomly received signal usually can be modeled as Rayleigh distribution. As you can see, there are towers, buildings like this, and this is a mobile unit having a receiver. Having a receiver, that means this mobile unit, not only a receiver, the mobile unit can work as transceiver. That means it can transmit as well as it can receive. For the timing, we are assuming that this mobile unit, this particular car, is receiving. This is for wireless communication. So the transmitter and the receiver are not wired, not connected via wire. So if somewhere over here there is a tower, just think of your handsets or think of wireless communication that you enjoy in your mobile sets. So if somewhere over here there is a tower and the tower is going to be transmitting the signal meant for this receiver, you see the signal from the tower can be received by this mobile unit through different paths. One could be this one, the direct path, if the tower is at this particular point. The second could be a reflected path like this. So the tower will receive the signal will get reflected by this building, and finally the reflected wave will be received by this mobile unit, right? So so through various paths, this receiver can receive signals transmitted by the transmitter. So that's why this phenomenon is known as multipath phenomenon. And if we consider that the mobile unit, this car is moving. Yes, it's a mobile unit, so it can move. Obviously, it will move. So what will happen if I consider this to be the direct path and this to be the reflected path? Suppose the tower is like this, though it's what I'm showing, it's basically out of proportion, but let's for the timing assume that this is the transmitter. So this is the direct path, this is the reflected path. If I consider these two paths, and if the mobile unit moves, then what could happen? See, so this is the direct path signal, this is the reflected path signal. So at certain points, these two signals, you see the direct path signal and the reflected path signals are in phase, here in phase. So they will add, and the composite signal will have a larger amplitude, and the signal strength received by the receiver will be very, very strong. SNR will be very, very high. But at certain point, what can happen? Suppose this is the direct path hmm, signal, direct path signal, and this is the received reflected signal. Sorry, this is the reflected signal. And in this particular condition, you see, suppose the mobile unit was at this particular point when the direct path signal and the reflected path signals were like this. Now it has moved to a different point over here, and at this point, these are the natures of the direct path signal and the reflected path signal. And since these two signals are 180-degree out of phase, hence the composite signal will be this one. That means one is actually cancelling the effect of the other signal, right? So at this particular position, what will happen? The signal to noise ratio will be pretty high, or the signal strength, if you think about the signal strength, then the signal strength will be very, very poor, very, very poor. And it might so happen that it will be complete cancellation will take place, and will not be able to hear anything, or in other words, the receiver will not actually receive any signal. The receiver will not be able to listen to the transmitter. Oh, on a regular basis, we face this particular situation, and this situation often, casually, we say that we are not getting the tower. We are not getting the tower. So actually, this is happening. So this is known as multipath phenomenon. And yes, if the mobile unit moves like this, so at a particular point, you see this is the amplitude of the received signal, and this is the distance traversed by the mobile unit. Okay, so at certain points there will be perfect addition of two signals. Okay, So the signal strength will be pretty high. At this point, the signal strength is has fallen from this value. At this point, complete cancellation has occurred, so will not be able to listen to the tower or listen to the transmitter, right? So we'll say that colloquially will say that we are not getting any tower. Anyway, so this envelope, or if you want to model this amplitude, and you see at which particular point cancellation will take place, at which particular point uh, these two signals will perfectly add up. This is absolutely random in nature. So this kind of distribution of amplitude received by the mobile unit is modeled by a random variable x, and this phenomenon is modeled with the help of Rayleigh distribution. That's why this phenomenon is often known as Rayleigh fading. Fading channel. And this particular phenomenon, if you want to model this particular fading, that means if you want to find out what is going to be the amplitude of the received signal, then we use a random variable which follows a Rayleigh distribution, and often this kind of fading is known as Rayleigh fading. Have you understood this? Is it clear?
Yes, ma'am.
So in final year, if you opt for another honors paper, which is communication principles, then in details you will be studying all these things. Anyway, okay. Did I send you the material? Okay. Now, first of all, tell me whether you have any query or any question or any doubt or not. Do you have any question? Hello, do you have any question?
No, ma'am.